Chapter 15, Quantum Translation, Section 15.4, the particle in the two-dimensional box. The Schrödinger equation for the particle in a two-dimensional box is this. We have the kinetic energy operator applied to psi equals E psi. The kinetic energy operator includes two parts. The kinetic energy operator in the x direction and that in the y direction. What about the potential energy of the particle? Well, it's zero inside the box. The potential energy, however, is infinity outside the box. Therefore, the wave function is zero outside the box because the particle can never escape out of this two-dimensional box. Now let's look at this figure. It shows the shape of a two-dimensional wave function for a particle inside a two-dimensional box. We have x from 0 to 1, y from 0 to 1. And over here, if you just look at the x direction, it goes up and down and up and down. So it's just similar to the wave function in one dimension. If you look at the y direction from 0 to 1, also it goes up, goes down, and up and down. And over here, you can see in the x direction, there are two wavelengths. This is one wavelength, and then you have another wavelength. Same here, one wavelength, two wavelengths. Now let's count the number of nodes over here. There's 1, 2, 3. 3 nodes in this direction. 1, 2, 3. 3 nodes in the y direction. So really, the two-dimensional wave function can be decomposed into two one-dimensional wave functions. One in the x direction, the other in the y direction. And mostly in the x direction, you'll have just the square root of 2 over a times sine n pi x over a. In the y direction, you have the square root of 2 over b times sine n pi y over b, where b is the length in the y direction. The position and momentum of the particle in the x direction are independent of the position and momentum in the y direction. Therefore, the solution to the Schrödinger equation of the two-dimensional particle in the box is this. The wave function of x and y is equal to a function of x times a function of y. The function of x is simply the one-dimensional particle in the box problem. It's the square root of 2 over a sine n pi x over a. In the y direction, it's the square root of 2 over b times sine n pi y over b. But we cannot use n here and also here because it is possible for the quantum numbers in the x and y direction to be different. So I'm using n sub x as the quantum number here, n sub y here. Well, of course, they can be the same as shown in this figure, but they can also be different. For example, n sub x can be 1, and then n sub y is 2. It is entirely possible for the particle to move faster in the y direction than in the x direction. And over here, it's just one example. When n sub x is 4, n sub y is 4, we have this kind of shape. For the particle in the two-dimensional box, we have the wave function of x and y equal to a wave function of x only times a wave function of y only. The x function is the square root of 2 over a sine n pi x over a. The function of y is the square root of 2 over b sine n pi y over b. Again, these two quantum numbers may be different, so we need to use n sub x and n sub y to denote the quantum numbers in these two directions. We can easily compute the second derivative of x divided by x, because the second derivative of sine theta is just negative sine theta. the second derivative of sine k theta is simply negative k squared sine k theta. So we can easily do this derivation. The second derivative of this x over x is this nx pi over a squared, and then we need a negative sign. Same here. The second derivative of the y function over the y function is negative ny pi over b squared. The reason we derive this is because it's more convenient for us to use this kind of equations when we try to determine the kinetic energy of the particle in the two-dimensional box. We apply the kinetic energy operator to the wave function this way, and then we apply this second derivative operator to x times y. We'll apply this second derivative operator also to x and y. But remember, this y is independent of x, this x is independent of y, and therefore we get this expression. It's negative h bar squared over 2m, and then the second derivative of x times the function of y, and also we have x times the second derivative of the y function. So we have this expression, and now we will divide these two terms by xy and then multiply by xy, so we have something like this. Alright, the reason is we're about to use these two equations. Alright, and then from here to here we have negative h bar squared over 2m. Now we have x double prime over x plus y double prime over y. They're provided here and here, and then multiplied by psi. Psi is simply the function of x times the function of y. Now we're going to just plug in the expression of x double prime over x here, y double prime over y here, and then we get this expression, and then we have the wave function of x and y here. We can clean this up a little. H bar is h over 2 pi. So h bar times pi is h over 2. So anyway, after we clean up, there are two terms inside this pair of parentheses. We have nx squared h squared over 8m a squared plus ny squared h squared over 8m b squared. So really, this is the kinetic energy of the particle in one dimension. This is also the kinetic energy of a particle in one dimension, but it's just in the y dimension with a box length of b. The energy of this two-dimensional particle is the sum of its energies in the x and y directions. The wave function of this two-dimensional particle is the product of these two wave functions, one of x, the other of y. They both take the form of the wave function of a particle in a one-dimensional box. Again, for the particle in the two-dimensional box, we have the wave function as the product of two 1D functions. This is a 1D function in the x direction. This is 1D function in the y direction. What about the energy? The energy is the sum of the energy in the x direction and the energy in the y direction. When this two-dimensional box is a square, that means A is equal to B, the energy of the particle in the square now becomes nx squared plus ny squared multiplied by h squared over 8ma squared. When we replace this b with a, when we have a square, now we observe energy degeneracy, because when nx and ny are equal to 1 and 2 or 2 and 1, we will get the same amount of energy. Now let's analyze more different cases. When nx is 1, ny is 1, the energy is 1 squared plus 1 squared times h squared over 8ma squared. So really it's this is the so-called 0-point translation energy for the two-dimensional particle. 0 point means lowest possible in quantum mechanics. Later you will learn the 0-point vibrational energy as well in the future. Now we see when nx is equal to 2, ny is equal to 1, or when nx is 1 and y is 2, the energy is the same, 5h squared over 8ma squared. It's called energy degeneracy. You have two different sets of quantum numbers, 1 and 2 versus 2 and 1. You get the same amount of energy. We say the degeneracy is 2. And this gives you the second lowest possible energy. And again, the degeneracy of this energy level is 2. What if nx is 2 and y is 2? Well, then the total energy is 2 squared plus 2 squared and then h squared over 8ma squared. And this is the third lowest possible energy for the two-dimensional particle inside a square. The degeneracy of this energy level is 1. Now you can predict the next energy level. Alright, starting from 1, 1, and then you have 2, 1, or 1, 2, and then you have 2, 2, and then what's the next one? Well, the next energy level is gonna be 1, 3, or 3, 1. So you have 3 squared plus 1 squared, or 1 squared plus 3 squared. You get 10h squared over 8ma squared with a degeneracy of 2. Because you can have two different sets of quantum numbers, 1, 3 or 3, 1. Again, if you have a square, then the total energy is n sub x squared plus n sub y squared times h squared over 8ma squared. Now I'm gonna show you the first 9 energy levels from the lowest to the highest. 1, 1, 2, 1, 1, 2, 2, 2. We talked about this. And then the next level is 1, 3 or 3, 1. We have a degeneracy of 2 here. And then 2, 3, 3, 2. You square 3, you square 2. Sum it up, you get 9 plus 4, 13. Over here, 1, 4 or 4, 1. Square them, sum it up, you get 17. 3 squared, you get 18. 2 squared, 4 squared, you get 20. 3 squared, 4 squared, you get 25. So the corresponding energies in terms of h squared over 8ma squared are 2, 5, 8, 10, 13, 17, 18, 20, and 25. And also you have the degeneracy 1, 2, 1, 2, 2, 2, 1, 2, 2, respectively.